Hello and welcome to this introductory video about Autodock Tools and basic preparations for molecular docking. So first of all, you have to install and run Autodock Tools, which are the part of NGL Tools, a larger package. You can do it in multiple ways depending on your operating system. Check the instructions or the official website of the developer. So when you install and run the Autodock Tools, first of all, you have to familiarize yourself with the basic manipulations and operations in these software tools. So let's open the test molecule, let it be a ligand, and check what we can do in Autodock Tools. So first of all, you have to open the molecule. Please go to File menu and read the molecule. Most likely you will have a default folder here, which is not really convenient. So I will teach you how to check the default directory, because at some point it will make you crazy. You have to once and once again change the directory. So go to File, Preferences, Set. Here you can define multiple options. And check this startup directory. So here you can set the directory that you would like, and you can put the working directory with your files that you are going to use for docking, and after this, press Make Default. And also set, it depends on whether you want to make it a startup directory only or a default directory. So each time when you will open and save files, software will offer you this directory. So make it default, set, and after this, close it. So now, let's go to File, Read Molecule, and open one of the molecules. For example, let it be phytotoxin. So we have it here. It's not really fancy looking because it's a linear presentation, but it can be easily changed. So how can we manipulate the molecules, our objects? The same as in ChimeraX, you can use mouse. So left mouse button is for the free rotation. Then right mouse button is for the translation, so for the moves. And middle mouse button is for the scaling, zooming in and out. Then here at the left part of the screen we have a dashboard, which is essentially the same as a module panel in ChimeraX. Here we have our objects. At the moment, there is only one of them, which is called phytotoxin, prepared. And please pay your attention to this set of operators. So first column S means select. So if you press here the empty circle, it will be selected. In ChimeraX, as you remember, the selection is marked with a green frame, but here it's with the yellow stars, or with the yellow crosses. Yes. After this, the molecule is selected and you can apply different operations to it. You should memorize from the very start that when you press here, it doesn't mean selection. So we don't see any selection stars here. So this is not enough just to click on the molecule to select it. You have to explicitly click this circle in the selection column. Only after this, the molecule will be selected. Please remember it. Then here L column stands for lines. So if we deactivate it, molecule will disappear because it had line representation. But we can now make it ball and stick representation, which is much better. Then we have here the C representation, which is for the van der Waals spheres. Then we have ribbons, but it won't work here because ribbons are calculated and visualized only for protein molecules. Then molecular surface. Here we can add labels. And the last column stands for coloring. So it opens additional window. And here let's apply some coloring. So we can make a custom color. Let's make it green. And after this, remember that when you work with molecular models, you always have to keep the standard coloring schemes. For this, select here by atom type. So now you know how to manipulate the molecule, how to change its representation. And now also let's learn how to change the background color. So different options related to camera view, to rendering, graphics are accessible via this 3D graphics menu. So this command set background color allows you to select any color for the background, anyone that you like, but I personally prefer white one. Okay, so what else do we have? As you see here in Autodock Tools, we have multiple different menus. At the very top of the screen, we have the horizontal main menu. Here we have File, 3D Graphics, Edit, Select, Display, Color, Hydrogen Bonds, Compute, Read 3D, and Help. File is obviously to read files, to save files, to import some files, open recent files, also to change the options, set preferences, browse some commands, load macros, and so on. 3D graphics menu is for the visual manipulations, for example, set anti-aliasing. For example, if you want molecules to be more smooth, you can modify it. You can change background color here, even make videos, render large images, which are of publication quality, because if you just make a screenshot, it will not be enough good to publish this picture. Then in the edit menu, you can make different modifications and apply different operators to the molecules. For example, you can delete everything. If you press delete all molecules, the program will warn you that now you're going to do something serious. Let's do it. So when you delete something, in most cases, it's not something that you can undo. So be careful. Besides this, you also can do various modifications of bonds, for example, add and remove bonds, modify type of bond, then delete all molecule, delete everything that you have, or delete all the selected atoms, delete hydrogens if you have them in your structure. And in the atoms menu, you can apply the Autodock force field to atoms. It's important for some types of work, and modify the type of atom and so on. You can delete water, compute charges, or explicitly set charges to atoms. Then you can add hydrogens, merge non-polar hydrogens, remove hydrogens, and so on. And also multiple other operations like fixing the missing atoms, because you know that structures downloaded from protein data bank, for example, they commonly miss some parts of structure. And you can fix these missing parts using this menu. Then you can apply different coloring again, so it's the second possible way how to color molecules. The same as in ChimeraX, here we can do the same manipulations in multiple different ways, which is very convenient. And also you can modify the torsional angles. Then select menu stands for the various operations that are applied to select separate atoms, residues, molecules, or everything at once. So you can set the selection level, whether it will be atom, residue, chain, or molecule. Then you can create permanent selections, and I will show it later. Then you can even store these selections. Then invert selection the same way as you did in ChimeraX. And also make more complicated selection, like select only specific atoms that you can explicitly write here, like a command. And you can also select only heteroatoms, for example, ligands, and define different spherical regions like zone around the ligand. It's similar to a common zone that we had in ChimeraX. Then in the display menu, you can modify the labeling, the visualization. So 3D graphic is more about the options, about the standard preferences, like modifying camera, but in display, you can manipulate the way the molecules are visualized, like show secondary structure, visualize surfaces, show balls and stick models, and so on. So multiple different ways how to change the molecular graphics visualization. In coloring, here you have again multiple different options how to color molecules, so it's a third possible way how to change coloring. In hydrogen bond menu, you can do various manipulations with hydrogen bonds, like predict them, calculate them, or you can even set explicitly the hydrogen bonds. You can add hydrogens, remove hydrogens here. Yes, modify the visualization of hydrogen bonds, for example, show them as cylinders instead of dashed lines, and so on. Then in the compute menu, you can apply various additional tools, which are plugins here. For example, you can calculate the electrostatic surface using an external software called APBS, and it's a very commonly used software for this goal in molecular modeling. You can build molecular surface using external tools here, and so on. It's very useful sometimes. Then also, this menu we will not use, because it's not necessary for the beginning. And in help, you can view documentation, check citation information, because if you publish anything done with the software, you have to cite it. So here you can get a proper citation for any of the tools, for example, for Autodock Tools. Then you have the so-called favorites menu, which is a set of commonly used commands. Here you have open file, save file, undo, redo, clear selection, then normalize view or go into default. It's the same as view all in ChimeraX. Then you can add current selection to a dashboard, so it means that you will create a permanent selection. Then you have the picking options. So here you have additional menu now. You can set options for Control key, Shift key, and select the level of picking. For example, you can pick on the separate atoms or residues. It's very convenient. The next option is for the commands, so we can also write Python commands to open this shell that I guarantee you will see multiple times because Autodock Tools fail very constantly and it will show you different errors. The next one is for messages. It's like a log. And also we have some additional options. If you want to make the graphic screen larger, you can press this float camera, and after this, turn it the whole screen. To go back, you have to deselect it. Then you have some additional user interfaces for different automation tasks. Then you can make the stereo view and make some additional options that we are not going to use in this introductory tutorial and in the exercises. And then we have a very important menu, which can be called the workflow menu, because it's a menu that deals specifically with the docking tasks. So it exclusively deals with the docking. Here in the ligand, you have different manipulations that are applicable for ligands, like opening ligands, select their flexible parts, detect roots, and so on. Then for flexible residues, if you have a fully flexible docking, you can here indicate which residues will be treated as flexible in the binding site. Then in the grid, you create a grid, which is used by Autodock, not by Autodock Vina. So we are not going to start with this. And then in docking, you can define different parameters that will be written to configuration files. It's also used by Autodock, not Autodock Vina. And in run, you can run different associated software like Autodock, Autodock Vina that we are going to do. Autogrid is an additional supporting tool that is used by Autodock. And finally, in the analyze part, you can perform the analysis of docking output from Autodock and Autodock Vina calculations. Okay, so that's enough about the menu. And now we're going to do some basic manipulations that we need to proceed with docking. So let's start our docking preparations, and let's learn two super fast and simple ways of preparing the proteins and ligands for docking, both for Autodock Vina and Autodock. So the easiest way to process ligand is to go to this ligand workflow part, input, and open. This will open the additional window, and here in the files type you can select the type of ligand. Probably you don't have PDB-QT. This is the format that is used by Autodock, Autogrid, and Autodock Vina. So you will face this multiple times during our course. But if you downloaded the ligand, most likely it has MO2 or PDB format. Let's select MO2 as for now and upload here our ligand. So here we have this phytotoxin that I downloaded from the working folder. Now you can open it. And you see a warning message. It states that the ligand was processed, its charges were saved, but if the ligand were missing charges, it will be added immediately. So it works in automatic regimen. Then it says that all non-polar hydrogens, and 17 of them were merged. It's for the convenience of calculations. Then some aromatic carbons were found, and 3 rotatable bonds were also indicated in this ligand. So it means that during the docking, this ligand will have 3 flexible pairs, so multiple conformations of ligands will be created on the basis of these flexible pairs. Press OK. So the ligand has been already prepared, and all you have to do is just save it. So go to Ligand, Output, Save as PDBQT. So one of the things that I want to mention right now is that when you are writing something, some name, and you save the file, it's very important to explicitly write PDBQT. Even if you see here that format is PDBQT, but if you don't write it here, it will be saved without any extension. It won't be acceptable for Autodock Vina or Autodock. So let's save it like this in our module 2. Yes, I also have it, but if you don't have it, just press yes. So this was the easiest preparation of ligand. If you want to select a more difficult way, if you want to control each parameter by yourself, so let's select the feed toxin and go to Edit, Hydrogens, Add, and select all hydrogens. So as you see, some atoms which stand for hydrogens were added. Then go again to Edit, Hydrogens, and Merge Non-Polar. And now we have to add some charges. Most usually, the Gasteger charges, it's one of the methods how to calculate atomistic charges. So most likely you will meet the Gasteger charges in publications, especially publications of previous decade, but it's enough for start. So you see the result, the total Gasteger charge was added. So this ligand is mostly neutral. Then you can apply the torsion, so detect root, and this is one of the problems that you will commonly meet if you try to do everything manually. So I recommend you personally to use this fast preparation route, because basically it does all the basic manipulations that you need. You can choose to root yourself by selecting one of the atoms, but we won't do it right now. And when you're happy with all the preparations, you can save the file the same way. Okay, so we can remove this molecule now. So let's delete it. And now how to prepare the protein. Again, there are 2 ways, the easy way and the more complicated way. The easy way starts with the grid menu. So here, grid macromolecule, open. Here select the file format, all files. And now we can select our protein. So for example, it could be the histone deacetylase, which you will have in the exercise. So let's open it. And the same way as was in the case of ligand, it will be immediately processed. And you have the result, so you can save it as a PDBQT. So just press save after you explicitly write here PDBQT extension. So it's very easy. So let's remove it and try more complicated way. So go to File, Read Molecule, and open it. It takes some time because protein is large. Let's change the visualization. Let's hide lines and show ribbons. And it can have problem if there are no secondary structure elements assigned, then you will have this problem. Chimera, which is her big advantage, can calculate secondary structure irrespectively of their PDB file content. Here, Autodock Tools cannot do it. So let's try surface representation. Yeah, it works. So the difference is that Autodock Tools reads secondary structure assignments from the PDB file. So for the models, for example, it doesn't work, but it calculates the surface. That's why surface representation works. Now let's select the protein and let's open its sequence. You can see that it has 2 chains. For example, we need only chain B, so let's select only chain A and delete it. So you cannot do this with the right mouse button. So for this, you have to go to Edit, delete selected atoms, and continue. So it will take some time. Yes, and now we have only chain B. And let's set the view to the standard. Yes. Okay, the same way you can modify individual residues. So if you open the whole sequence, you will see all of the residues that you have here. Ligands usually are in the variant, if any of them are present. Here, for example, we have zinc atom, potassium. For example, we want to color zinc atoms in green color. For this, we can apply custom coloring scheme. Let's show it first as a sphere. And let's make it green. And to see that it's really green, we have to hide the surface. So deactivate surface here. And now, okay, we have our secondary structure finally. And here we have the zinc atom. So when you selected the zinc atom, there are different ways how to clean the selection. Easiest one is to press this button, clear selection, or the other option is to just tick this button for selection again, and the atom will be unselected. So now let's try showing the local environment of zinc atom. So now we have selected it, and you see there are some dots showing that it's selected. Now go to Select, Spherical Region, and here let's set 4.5 around. Okay, let it be like this. Okay. Yes, so you have to specify the center from which these 4.5 angstroms will be calculated. So for this, select current selection, then set the cutoff distance, all molecules, and select. Okay. Now you see that some of the atoms were highlighted. And now if you move up, you will see that, for example, this aspartate 264 is selected because it has a mark here. It's in part selected on some atoms. So now we can save this selection. It can be done the same way. Let's select it here. Yes, so now this set can be manipulated on its own. So we can, for example, show these atoms as ball and sticks, apply some coloring to them by atom type. Okay, good enough. Then to prepare the protein, let's reset the view. We have to make some modifications to it, like add hydrogens. Let's add only polar hydrogens this time, so we don't have to merge them. So let's remove this spheres representation, so they will be represented only as lines. Okay. Then we have to calculate the charge. Let's compute the cascading charges. It's close to -2. Then let's assign the Autodock force field to atoms, so they will be typed with the force field. And after this, you can save the file as a PDBQT, the same way as you did before. Here you can select which columns to save, which lines to save, but you can keep it by default. So by default, only the most important lines like atom, heteroatom, connect, sheet, and helix will be saved. Here you can select where to save your file, the name of it, and then press OK, and it will be selected. So it's the more sophisticated way of doing the same. Okay, let's again clean everything. Yes, let's delete everything. Then, how to figure out the coordinates of the docking box? For this, again, let's vote the molecule. You need a protein as the target for docking. So we have our protein here. Let's show the secondary structure for it. Then let's find our zinc atom, because we need to know its coordinates. Let's focus the view on it. So for this we have to select it and then show in 3D view. So now it will be set as the center of screen. And then show it as a sphere. Okay. And now we will prepare docking box. So for this go to grid box. It will be shown immediately. And it can be easily manipulated using these wheels. You see that you can change the size in 3 dimensions. Here you can set the center. So let's make it around zinc. Like this. Good. And then make it not so large. Like this. So we have to move it slightly here in this direction. Yes. So now we can make it smaller. That should be good enough. So you can copy the coordinates from here and pass them into the command line when you will run Autodock Vina. Or if you use Autodock, here you can save this grid box. And now I'm going to show you how to run Autodock Vina from the command line. If you use Windows, as for me, the easiest option is to download this CMD application that you have in your working files and then explicitly put it to your working folder. So for example, here I have this CMD. And here I can write different commands. So you can copy and paste that command that I provided you in the instructions. But to execute the actual docking, you have to have all of the necessary files in the same folder. So here you have to have here this phytotoxin file, which is used as the ligand. It should be in the PDBQ format. So here in the working files for exercise 2.1, you can download the cmd.exe and then execute it right from the folder where you have everything. So you can double click on it and then you have the command line where you can write different commands. So now let's copy and paste the command from the instructions. For this we have to open the instructions for the exercise 2.1. Let's scroll down a little. And here we have, yes, we can use this command, we have it here. So you can copy it and then go to the command prompt. And paste it here. Just to use the ordinary Ctrl+V. And now you can press enter when you have the whole command. Some mistake, we have to correct something, I guess. What could go wrong? Oh, I missed the ligand here. When I was copying, I missed the ligand. Now it should work. Yes. So it's working. The Autodock Vina says that output will be named this way. Usually the naming is based on the name of ligand with the addition of out. Then it says that it has read the input successfully, set up the scoring function, analyze the binding site, use the random seed, and now you see that search process is performing. It usually takes just 1 minute with such settings that we have. But if you increase exhaustiveness, so make the search more thorough, it can take up to hours. So it really depends on the size of the system, on the number of rotatable bonds, the size of protein, the size of docking box, and on the exhaustiveness. Okay, so it's 4, 3, 2, 1, and it's ready now. Okay, here you see the table with affinity score. The lower the affinity is, so the more the negative value here, the higher is the affinity. So mod number 1 has the best affinity because it's the most negative. And here we have the root mean square deviation of each of the poses starting from the second, comparing to the top pose. Now let's open ChimeraX and make a basic analysis of the docking output there. Finally, we are in ChimeraX, and now we are going to do a basic analysis of the docking output from Autodock Vina. For this, first of all, you have to load the protein or the receptor. In our case, it's 5-ICNB. I have it here recently loaded, so I just open it here. And now you have to open the same way the output file, which has out PDBQT format. For this, you have to locate it on your hard drive. So it should be file with out PDBQT. So it's this one. And the poses will be immediately loaded here. Okay. So just from the very start, you see that we have 3 clusters of poses. The dominant cluster with most of them, 7 out of 9, and 2 additional clusters with only 1 pose. And now let's go to Tools, Binding Analysis, ViewDockX. It's a special graphical user interface that allows you convenient analysis of the docking output. So here you have a table in the right bottom part of the screen, table with the predicted poses of phytotoxin in the binding site of histone deacetylase 1. We have 9 poses predicted here. It can be modified. You can have 20 poses, for example, but by default it's 9. Then you have ID, and as you see in the model panel, each of these poses was also loaded as a separate submodel. And it has ID 2.1, 2.5, and so on. And you can manipulate each of them individually. So let's hide all of them by pressing this square and see only the best pose. So this pose has the best score, the same as the second one. So 2 of them have the highest score, and you see that poses are different, but they are in the same cluster. And also this interface allows you to add hydrogen bonds. So ChimeraX will calculate hydrogen bonds using its own calculation algorithm. And now we see that for each of the ligands, here the H bond column was added. And we see that some of the poses have H bonds while others not. The same way we can calculate the clashes. And you see that none of the predicted poses have any clashes with the protein. So let's have only the first top ligand here. It has 1 H bond with the cysteine number 100. So you can manipulate it here, you can select it, for example, center the view on it using graphics that you selected. So everything else is removed now. Make the white background, add silhouettes. Looks very good. But even more, you can select this individual pose using the Save button, and it will be saved as a Mode 2 pose. Then also you can add some plots. For example, you can build a plot that shows dependency of affinity, which is called score here, which shows the correlation or dependence of affinity on the number of H bonds. And you see that there is no real correlation. So for example, we have 4 poses that have 1 H bond, but 2 of them have high score and 2 of them have low score, so no correlation. And also you can make a graph here. If you press the graph, you can visualize some of the parameters here, some of the features like H bonds, clashes, and score. So you can see how well these parameters agree with each other. It's a very convenient graphical user interface, which will help you to make basic docking output analysis. And basically, it's all that I wanted to show you here. So I hope that everything will work. But if you face any problems, if something fails or doesn't work, please send me an email or post your questions to a discussion forum. And good luck with the docking.